In this chapter, we will take a look at complex numbers and the theory of equations. We will start with the complex numbers. Historically, the number system was introduced to solve equations and to find the root of polynomials. Over time, the number system has been expanded. The first set of numbers were the natural numbers, indicated by the letter n, and so they consist of all the numbers 1, 2, 3, and so on. However, this set of numbers was inadequate to solve certain equations. So it was inadequate for equations of the type x plus n equal to m, with n and m both natural numbers, such as, for example, x plus 3 is 2. The solution of this equation is of course minus 1, but minus 1 is not part of the natural numbers. And so the natural numbers have been expanded and the integers have been defined. So the integers, indicated by the letter z, are basically the natural numbers plus 0 plus all negative natural numbers. So z is Still, this was not sufficient to solve all equations. So think, for example, of an equation n times x is m, where n and m are both integers. Then you still have certain equations which you cannot solve. So for example, 3 times x is 2. So the solution would be 2 over 3. So we have fractions which are not included in the integers. When we go to the rational numbers, so the rational numbers indicated by the letter q, this is basically z plus all those fractions which are not included in z. So we can write q as the m over n, for which m and n are both integer numbers and n is not equal to 0. So this includes all the natural numbers, this includes all the integers, and it also includes all the fractions of integers. But still, this set of numbers does not allow us to solve all equations. So think, for example, of a quadratic expression, x squared equal to 2. The solution of x squared equal to 2 is the root of 2, which is not a rational number. It is a positive number, but it can never be expressed as a fraction m divided by n. And so people or mathematicians have added all those extra numbers, and they call those the real numbers. So the real numbers is the set q, the q over the rational numbers, with all the irrational numbers. So every number that cannot be expressed as a fraction m divided by n. For a long time, the real numbers were sufficient as a set of numbers. However, as mathematics and physics got more complex, we were also confronted with other types of equations. So for example, equations x squared equal to minus 1, which do not have a solution within the real numbers. And so again, the real numbers have to be expanded. There was a larger system needed than just the real numbers. To this end, the complex numbers were introduced. So we denote them by a C. C is the set of all complex numbers. We will denote a complex number as a plus b times I, with both a and b a real number, and I being defined as the root of minus 1. In this expression, a is called the real part, b is called the imaginary part, and then I is the imaginary unit. We indicate complex numbers often with the letters z or w, and then we write, for example, z is x plus yi, then x is the real part, so we will denote the real part as re of z, and y is the imaginary part, im of z. If we have two complex numbers, so z is x plus yi, w is a plus bi, then they can only be the same, so z can only be equal to w if the real parts are the same and the imaginary parts are the same. So if x is equal to a and y is equal to b. Note now that every quadratic expression has a solution in C. So within the realm of the complex numbers, every quadratic expression can be solved. Take, for example, x squared plus 4 equal to 0. So this clearly has no real solutions, so no solutions in R, but it will have a solution in C. So x squared plus 4 is 0, also means that x squared is minus 4. So x is either the positive or the negative root out of minus 4, equal to the positive or the negative root out of 4 times I squared. So it is either plus or minus 2i. And so it has two complex solutions, but no real solutions. Since any complex number is written as x plus yi, so basically we have a pair of real numbers. So we have on the one hand the real part of z, which is x, the imaginary part of z, which is y. X and y both are real numbers, and so we have a pair of real numbers that can be used to represent z in a plane. Which brings us to the graphical representation of a complex number. This graphical representation is called an Argand diagram. And just plots the complex number in a plane. So you have a plane, you have an x-axis and a y-axis. In this plane, the x-axis represents the real part. It's the real axis, and so we will indicate the real part of the complex number on this axis. The y-axis will correspond to the imaginary part of the complex number. If we then plot the complex number z in the Argand diagram, so in this plane, we see that the real part of z is x, so this is the value that z will have on the x-axis. The imaginary part is y, so this is the value that z will have on the imaginary axis. So here again, the x-axis corresponds to the real numbers. So basically all values x is x plus 0 times y. The y-axis are the imaginary numbers. So yi is 0 plus y times I. As an example, let us plot some numbers in the plane. So let's say we have z1 is 3 plus 2 times I. We have z2 is minus 2 minus I, and we want to plot them in the complex plane. So we start by drawing the plane, the real axis and the imaginary axis, and then we look at the different components of the points. So for z1, the value on the x-axis is the real part, so it's 3. The value on the y-axis is the imaginary part, which is 2. So you have a point z1, which will have x-coordinate 3, y-coordinate 2. For z2, the x-coordinate is minus 2, so we are on the negative side. Same thing for the y-coordinate, it is minus 1. So also on the y-axis we have a negative value, and we have a combination minus 2, minus 1, which corresponds to the point z2 in the Argand diagram. Let's now assume we want to plot the set T, the set of all complex numbers, so all a plus bi, but with two conditions. We want to have that a is no more than 1, so it's strictly smaller than 1, and b is positive. So again, first we plot the Argand diagram, we plot the plane. On this plane, then we know we want to indicate all the numbers which have a real value strictly smaller than 1. So 1 will be a boundary. The one on the x-axis will be a boundary, but it will not be included. And then the second condition, b is at least 0. So this means my second boundary will be the x-axis, but in this case the x-axis will be included because b can also be 0. And so we get the part which is indicated in red on the Argand diagram, which corresponds to all complex numbers that are in the set T. Sometimes it can also be very useful to use polar coordinates in the complex plane. Polar coordinates have been introduced shortly before, but what we need for polar coordinates are on the one hand a distance and on the other hand an angle. So we need the distance from the origin to the point, which we call the modulus of z, and we have the angle, so the angle between the x-axis and the modulus. This angle is called the argument. So if we bring this to the plane, to the Argand diagram, the modulus is the distance from the origin to the point z, and then the angle between the x-axis and this line is the argument theta. The modulus will be indicated with letter r, so r is the distance between the origin and the z point, so we also write this as the absolute value of z. So an absolute value for a complex number is a distance, it is the line between the origin and the point, so also written as the modulus of x plus yi. And then using trigonometry, we see that this distance is x squared plus y squared, and we take the root out of this. So a modulus is a distance, so it will always be a real number, and it will be non-negative. And as I said before, it's also called sometimes the absolute value of a complex number. The argument, on the other hand, is an angle. So here we have the argument of z is the angle theta in such a way that the tangent of theta is equal to y divided by x. There is a remark to make for theta. So we know that tangent has a periodicity. So we have multiple solutions if we do not specify this angle. And so we will go for the principal argument, which means that we choose theta between minus pi and pi. With these definitions, we get that x is r times cosine of theta, y is r times the sine of theta, and z is x plus yi. This is equal to r times cosine theta plus I r sine of theta, and this representation is called the polar representation of the complex point. Let's then apply this polar representation for some examples. So for example, we have the point 2, z is 2. In this case, we know that the modulus of 2, this is just 2 itself, and the argument of the point, so the argument of 2, will be 0, because the point 2 is on the x-axis, so there is no angle between the x-axis and the modulus. If we take z is 1 plus I, then we know that the argument, or we can calculate the argument of z as being the root of 2. So it's the root of x squared plus y squared. It's 1 plus 1 is 2, we take the root out of it. And for the argument, we just take a look at the plot, so the argument of z. If we draw this, we see that the tangent of theta is 1, and so the argument, the angle itself, will be pi divided by 4. If we have a purely complex number, so z is, let's say, I, then the modulus of z in this case is 1. It is the distance on the y-axis, so it's 1 up. And the argument of z, it's on the y-axis, so the angle between the x-axis and the y-axis is pi divided by 2. Let's assume z is minus 2i. Then again we can look at the argument of z. argument of z is easily calculable as being 2. So the absolute value of minus 2i is 2 again. And the argument of this z, it is on the y-axis, but it's on the negative side. So we have an argument of minus pi divided by 2. Let's now take z is minus the root of 3 plus I. The modulus of z is easy. So this is just the root of 3 squared, so it's 3 plus 1. You take the root of it, which is 2. The argument of z will be a little more difficult. So we have here theta. We have an argument, an angle. And for this angle, we know that the tangent of theta, so this argument is theta, the tangent of theta is y divided by x. So it is minus 1 over square root of 3. So what you can do to solve this is look at the complex circle. So we apply some trigonometry. We have a complex circle. We see here that the point will be in the second quadrant. So it is in Q2. Why? Because my x value is negative and my y value is positive. If you then look in the second quadrant, which angle has a tangent value of minus 1 over the root of 3, this will be 5 pi over 6. So remember, your angle always has to be between minus pi and pi. Similarly, take z is minus 1 minus 2i. The modulus of z is again easy. So here we have 1 plus 4. We take the root out of it, so it's the root out of 5. The argument of z is again theta, such that the tangent of theta is y divided by x. So it is minus 2 over minus 1, which is 2. In this case, we know that the angle will be somewhere in the third quadrant, so in Q3. Why? Because if I look at my complex circle, my y value and my x value both are negative, so we are in the third quadrant. However, it is not very easy to determine which theta will have a value equal to 2. It's not one of the regular angles, one of the known angles, and so we have to work differently. So what you will be using is the inverse of tangent, so tan minus 1, but it's very important here to note that tan minus 1 is only defined between minus pi over 2 and pi over 2, so it will give me an angle in Q1 or Q4, but not in Q3. So we have to apply some trick, some modification of the angle. We know that my angle theta will be somewhere here, so this will be theta. We know that for theta, the tangent of theta is 2. The other angle for which the tangent is 2 is this angle. So it's the angle in the first quadrant. Let's call it beta. Then we know that the tangent of theta is equal to the tangent of beta, which is 2. But we can define beta as being the inverse tangent of 2. So this one is known because it is between minus pi over 2 and pi over 2. If we then look at the relation between theta and beta, we see that theta is just minus pi plus beta. So it is minus pi plus tangent minus 1 of 2. We can do the same thing for the previous one. So the minus root of 3 plus I. We know here theta is this angle. But again, we cannot use the inverse of the tangent because the inverse of the tangent is only defined for angles between minus pi over 2 and pi over 2. So we apply the same reasoning. If we take this angle, so we do a point image across the origin. So this angle beta. For this one, we know that the tangent of theta is equal to the tangent of beta is equal to minus 1 over 3. We then know that beta is tangent minus 1 of minus 1 divided by 3, because beta is between minus pi over 2 and pi over 2. What then remains is to find the relationship between theta and beta, and for this we see that theta is just pi plus the angle beta, because beta is a negative angle, so if we do this, pi plus beta, we find theta. In conclusion, to find the argument of some complex number, it's best to make a quick sketch of the complex circle, and then see in which of the quadrants it has to be lying, and use the trigonometric rules for the angles to find the correct angle. the correct argument. If we have a complex point, z is x plus yi, then the conjugate of this point is defined as z bar x minus yi. So the conjugate of a point, of a complex point, is the point which has the same real part, but the opposite of the imaginary part. So it is x minus yi instead of x plus yi. And now we indicate this as z bar. So we draw a line above z. And in that case, we know that z and z bar are each other's conjugates. So we see that the real part of z is the same as the real part of z bar, and the imaginary part of z is minus the imaginary part of z bar. If we plot both z and z bar, it's very easy to see that the modulus remains the same. So the modulus of z bar is the modulus of z, and the argument of z bar is minus the argument of z. Why? Because actually the conjugate is just a reflection of the point across the x-axis. Then we can also note that z is equal to z bar only if z is a real number, and z is equal to minus z bar only if z is purely imaginary.